So it's my pleasure to introduce Diane Maclagan from the University of Warwick, who's going to speak on toric and tropical Bertini theorems in arbitrary characteristic.
Okay, so thanks, Jesus, and thank you, well, to the whole ZAG team for the invitation and to the audience, for all of you for showing up. So I'm going to be, as the title says, I'm going to be talking about toric and tropical Bertini theorems in arbitrary characteristic. And this is joint work with a big team of, so Francesca Gandini, Milena Herring, Fatemeh Mohammadi, Janet Rashcott, Ashley Wheeler, and Josephine Yu. So let me, just to get us on the same page, and sorry, actually before I say that, I should say, please do ask questions. I should be able to see the chat, but hopefully Jesus will let me know if I'm missing anything, or speak up. So let me start with first, this is the cartoon version of the talk. So we have over here on the left, our classical Bertini theorem, that I assume most of us know, my variety intersecting with a hyperplane. And I'm going to discuss in this talk two different generalizations. One, a toric one, where I'm going to, instead of intersecting with a hyperplane, I'm going to intersect with a subtorus, if my variety lives in a torus. And another one, a tropical one, where I'll have a tropical variety. I'll tell you what I mean for those of you who are not tropical later, intersecting with a hyperplane. Okay, so anyway, so that's my cartoon, talk over, we can, summary of the talk, we're all done. But to actually give some details, to check that we are all on the same page, let me remind you of what I mean by the classical Bertini theorem. So we're going to start with an irreducible subvariety projective space over an algebraically closed field of dimension at least 2. And then the result is that the set of hyperplanes in projective space, for which when I slice my variety with these hyperplanes, I still have something irreducible. That set of hyperplanes I want to think of as dense in the dual projective space. And I'm stating it this way because to make it easier to see how the generalizations fit. I mean, of course, there are other versions of this. I mean, most notably, perhaps, is if we generalize irreducible to smooth. But for the applications I had in mind, I want to focus on the irreducibility. Okay. As we all know, this is sort of key for induction proofs. I mean, in some sense, it's so key that it often gets swept under the rug. I think as a student, there were a bunch of proofs I would find really confusing. It's like, why are they saying without loss of generality, I can assume that my variety is a curve or some points? And so it's so key that we just sort of put it under the rug and assume it. But in this talk, I want to talk about two variants. The first is I want to replace my subvariety of projective space by a subvariety of a torus, and replace H by a subtorus. Okay, that was the middle column of the cartoon. And the second is I want to replace X by a tropical variety. So I want to replace X by its tropicalization. In that case, we'll still keep the same hyperplanes. And we'll see that there are issues with both of these, but we do have. Okay, so let's start with the toric one. So we want to start with a subvariety of the torus, and we want to replace H by a subtorus T prime. So my algebraic torus here is K star to the N. So K star being K take away the origin. So that's the algebraic torus, algebraic group. And we're going to look at a subtorus T prime and intersect X with T prime. There's an issue, however, that we can't expect most T prime to work, right? Classical Bertini, you're saying most hyperplanes, when you slice them, you get something irreducible. We can't assume that for in the torus case. So to illustrate that, I just want to do a really concrete example. If I start with a hypersurface given by x squared minus yz squared in a three-dimensional torus, choose your favorite field, K, you will notice that this is actually secretly a subtorus itself. This is a two-dimensional subtorus. If I take the subtorus, another two-dimensional subtorus, T prime, parameterized T1, T2 squared, T2. The intersection of X with T prime, just in the coordinates on T prime, I just substitute in X is T1, Y is T2 squared, Z is T2. I get the variety of T1 squared minus T2 squared times T2 squared, which we can see difference of two squares. This is irreducible. So this is reducible, I should say. So we've sliced it. So that's one example. The problem, though, is that this is not, I mean, it's easy to come up with examples. So I can just generalize this example by replacing 1, 2, 1 by A, 2, B, C. So my subtorus is now T1 to the A, T2 to the 2B, T2 to the C for any A, B, C in Z cubed. I do the slice again, X intersect T prime, and I get the variety of T1 to the 2A minus T2 to the 2B plus 2C. Again, it's a difference of two squares. We have a reducible variety. Okay? And you can see the problem here is that this is going to be, we're going to get such an example for any choice of A, B, C in Z cubed. And already, you only expect, the character lattice of the three-dimensional torus is itself a Z cubed. So the set of tori that don't work are somehow commensurate with the whole torus. So that's the bad news. Okay. The good news is that there is a way around this. And this comes from a paper of Fuchs, Mantova, and Zanier based on earlier work of Zanier. So this appeared in JAMS 5 years ago. And the idea here is we want to rule this out. And the way we're going to do this is we're basically, so instead of saying I'm going to take my variety and slice it with a subtorus, I'm going to project my variety dominantly onto a torus. So by a finite map, so my torus is the same dimension as the variety, and then take the pre-image of a subtorus. And we're only going to accept certain maps, such dominant maps. We'll say that pi satisfies PB for pullback if the pre-image, if the pullback along any isogeny of T to the D remains irreducible. So I start with X being reducible. I want to start with X being irreducible. I want to pull it back along an isogeny. So isogenies, the torus again is an algebraic group. So this means we want a surjective group homomorphism with a finite kernel. In coordinates, you can choose coordinates so that these are all going to be something like T1, T2 goes to T1 cubed, T2 to the fifth, something like that. And you want these to always, the pullbacks always to remain irreducible. Okay. So you can see, and those are going to be the sort of things we're going to look at. You can see from the previous slide then that x squared minus yz squared projecting onto the first two coordinates does not satisfy this PB. Okay, and one way, well, we can see it directly by modifying the previous example. If we take the isogeny that sends xy to xy squared, taking the pullback just means substitute in y equals y squared here, and then we get something, all the exponents are even, it's again reducible. Okay, so that was an example of something that doesn't satisfy PB. It's not hard to come up with other examples that don't, modify all of the other previous examples, but it's also not hard to come up with examples that do. So your expectation should be that, this is a restriction, but it's not a serious restriction. Once we've made this restriction that we're going to look at these dominant maps that do satisfy PB, then the Fuchs-Mantova-Zanier result tells us that there is a finite union of bad subtori such that if T prime is a subtorus not in this bad union, this finite union, then the pullback of any coset will remain irreducible. Okay, so this is, I can see Martin Sombre in the audience. This is also extended in work of Sombre and some collaborators to be a bit more explicit about how this works. Okay, so what's the idea is if you say, so I said, well, okay, we classical Bertini, you intersect with almost any hyperplane, it remains irreducible. If you want to replace hyperplanes by tori, you run into trouble. It's easy to come up with lots and lots of tori that are bad. But if we rephrase the problem as take the pullback of a subtorus and make it satisfy this pullback property, then we do get there's only, you get a finite union of subtori to avoid. Okay, and the coset is because maybe you don't want the preimage of a torus, but you want to intersect. In the same way, if we were in affine space, you might not want to think about hyperplanes through the origin, but affine hyperplanes. So the coset is the torus equivalent of that. Okay, so that's the result. Very nice, published in JAMS 5 years ago. From my perspective, though, from the applications I wanted to use it for, there was one issue, and that's that it's written for the paper is written for the complex numbers, and the proof really does require characteristic 0. Okay, if you look at the proof naively, you see that there's some resolution of singularities. But I think more serious is some of the Galois theory in the proof is assuming is not going to work in all arbitrary characteristics. So it's not the case that someone comes along and proves resolution in characteristic P, and suddenly this result holds an arbitrary characteristic. It's a side product of proving a bound of one of those very nice, bewilderingly elementary questions, which is the following: if I give you a polynomial f in 2 variables, x and y, and I ask you, what can you tell me about possible polynomial roots for this? By which I mean, for what are the possibilities for polynomials y equals g of x? So we're going to have y of f of x comma g of x equals 0. If I tell you the degree of a bound on the degree of f, can you give me a bound on the number of terms of g? So proving that bound is actually the main result of the Fuchs-Mantova-Zanier paper, and the Bertini theorem comes out as a corollary of some of the methods. But there's you cannot, the Fuchs-Mantova, this headline result about bounding number of terms of a polynomial is just false in characteristic P. There is no bound. So we can't just generalize their techniques and suddenly get a proof in arbitrary characteristic, even if we had resolution in characteristic P. Okay, so that's where we are. We have this is very clean, nice result in characteristic 0, doesn't obviously extend to characteristic P. Okay, I'm going to pause. Any questions before I go on? Since that's the end of the introduction to the toric Bertini theorem part. Can also come. Okay. Well, let me tell you first then about the tropical Bertini theorem. So this was my motivation. And so before I do that, I should tell you, what do I mean by tropical geometry, since there are several different approaches. And so here I'm going to think about a subvariety of a torus. Again, I'm going to work over an algebraically closed field. This time it's going to be a valued field, so there's a rank 1 valuation. The tropicalization of x is going to be then essentially the image of x under the valuation map. So I've chosen coordinates on my torus, k star to the n. So that means a point of x comes with coordinates x1 up to xn. And I can just take the value, apply the valuation to each of those coordinates, val x1 up to val xn. That gives me a point in Rn. And I can do that for all points in my variety. That gives me a collection of points in R to the n. And the miracle, kind of what makes tropical geometry work, is that this is not just some arbitrary subset, but it has a lot of structure. So in general, it's going to be the support of a polyhedral complex. So I've drawn some sketch pictures in the bottom here. The idea here is that a polyhedral complex is going to be just a union of polyhedra that intersect nicely along faces. Support means we don't mind if you subdivide them. We only care about just the union of these as sets. So if X is irreducible, so that's true, I guess we should say, if you do this for any variety, irreducible or not. If X is irreducible, then the tropicalization is furthermore connected, and it's pure of dimension, the dimension of X, by which we mean in each of the polyhedra, the maximal dimensional polyhedra that show up all have the same dimension as X does. So it's a combinatorial shadow here of the original variety. Okay, so here are some pictures at the bottom of the tropicalization of curves in the plane. Okay. Should maybe say this theorem has it's kind of, for non-tropical people, this theorem has an interesting history in that the observation that we get a polyhedral complex actually goes back to Berry and Groves in the 80s. That they were working in geometric group theory. This is about 20 years before tropical geometry in this form even existed. Definitely more than 20 years before the name tropical geometry existed. So in the modern era, in this century, the observation that when X is irreducible, it would be connected, that comes from first observed in work of Bogart, Jensen, Speyer, Sternfels, and Thomas. There was a slight gap in that in part of the connectedness proof that was fixed and expanded upon by Cartwright and Payne. Okay, so that's tropical geometry. If you're not a tropical geometer, you just think I take X and I give you back this combinatorial shadow, a picture like this, a union of polyhedra in the plane. And the idea is that the geometry of these pictures should reflect some of the geometry of the variety, at least when we're lucky. Okay, so Josephine, you and I were motivated originally, actually maybe I should say one more word about this. We were originally motivated to actually see when X is higher dimension to sort of improve on this connectedness result. So we have a result that actually gives you a higher connectivity in the sense, this is in the sense of graph theory rather than homotopy theory, for tropical varieties in the case that X, they're the tropicalization of an irreducible variety. And to prove that though, we wanted to do a proof by induction, come back to the base case where we know that tropical curves are connected. And so we wanted to be able to take a tropical variety, slice it down until we got something that looked like the tropicalization of a curve. So, and to do that, our original proof, using the slicing, we had a tropical Bertini theorem that actually relied on the Fuchs-Mantova-Zanier paper, so relied on characteristic 0. And then we joined the rest of the team, so Gandini, Herring, Mohammadi, Rushcott, and Wheeler, to get arbitrary characteristic. Okay, so what do I mean by a tropical Bertini theorem? So this looks closer in a sense to the classical Bertini theorem. I've got something that's the tropicalization of a torus over an algebraically closed field. Sorry, a tropicalization of a subvariety of a torus. Here I'm working over an algebraically closed field. And here X is irreducible of dimension at least 2. And what I want to see then is I want to look at the collection of rational affine hyperplanes in R to the n, that when I slice it with sigma, I get the tropicalization of an irreducible variety. And it turns out that these are dense in PNQ, in projective space. Okay, so I'm thinking of projective space over the rationals as parameterizing my affine hyperplanes in my affine rational hyperplanes in R to the n. Yeah. And so this is the tropical Bertini theorem, where same statement as the classical one in the version I stated it for you, just with x replaced by trop x, and we're still getting the same thing. So this answers a question of Cartwright and Payne, because the BJSST connected this result, tried to, sort of the gap was in some sense assuming that when we sliced with a hyperplane, you got something irreducible. This was caught by Cartwright and Payne, who fixed it by replacing it by basically classical Bertini. So we used the tropicalization of a classical hyperplane, which is a more complicated object. But then they asked, well, does the original proof work? Could we use a classical hyperplane? And this is where we're saying the answer is yes. Okay, so that is the the Bertini theorem. And I guess, as I said, we were originally motivated to use this, I mean, as a classical algebraic geometry. You want it for an induction proof. You want to be able to reduce your result about tropicalizations of irreducible varieties to tropicalizations of curves. Yeah. Okay, so I guess again, pause for any questions or comments. Yeah. Okay. Obvious question. I've hinted at the answer, but maybe it's still not quite clear. I mean, if you're not a tropical person, maybe this is the thing to take away from the talk, is what do these topics have to do with each other? So the answer is that an affine rational hyperplane is the tropicalization of a coset of a subtorus of my torus. Maybe this is easiest to explain in an example. If I have a hyperplane like 4x plus 5y minus 3z equals 1, that's the tropicalization of a variety ex to the fourth times y to the fifth minus alpha z cubed, where alpha is anything with valuation 1. So the idea here is, I mean, the mantra of tropicalization, for those who haven't seen it before, is you turn multiplication into addition and addition into minimum. And normally here, so I can see that I have, so if I divide this, if I turn this into x to the fourth, y to the fifth over alpha z cubed, I would get that tropicalizes when multiplication turns into addition to 4x, 5y, 3z, and then a 1. Okay, so that's the hyperplane. But you notice that this is also a coset of a subtorus. Okay? If alpha were just 1, this would be actually a subtorus. And one way to parameterize it is it's the subtorus t1 cubed, t2 cubed, t1 to the fourth times t to the 2 to the fifth. So it's the image of a two-dimensional torus under this monomial embedding. So this is embedding the two-dimensional torus as a subgroup of my three-dimensional torus. Okay, so you just have to check that, hopefully I didn't make an arithmetic mistake, that this to the fourth times this to the fifth equals this cubed. Okay, with alpha equals 1, we're just taking a coset. And I just chose one. I mean, you could write this many different ways, but I'm taking the coset where I just multiply this by the fourth root of alpha, 1, 1. Okay, so the idea again is affine in rational hyperplanes are tropicalizations of cosets of a torus. Okay, and so roughly we want to think about the tropical Bertini theorem as a tropicalization of this Bertini theorem for the torus. Okay, so the general idea is for sufficiently general alpha, so I had my coset alpha, so sorry, here we have the coset alpha. So for sufficiently general alpha, the tropicalization of x intersect alpha t prime, that's the tropicalization of x intersect the tropicalization of alpha t prime, which was my hyperplane H. And so if I want to know that this is the tropicalization of a an irreducible variety, it would suffice to know that x intersect alpha t prime was the tropicalization of an irreducible variety. Okay, and that's why, so that's why we want a Bertini theorem for the torus. For me personally, it came backwards, right? I wanted to know a tropical Bertini theorem. We were like, oh, wouldn't it be nice if there was already a toric Bertini theorem? And then at the time, this was several years ago, when Josephine and I started the project, it was, oh, that was actually just proved a few years ago. So it was one of those very timely moments in mathematics. Okay. Punchline of this talk from our perspective is, so this is again with the team, Gardini, Herring, Mohammadi, Ratchcott, Wheeler, and you that we do have a toric Bertini theorem holding an arbitrary characteristic. Okay, so this is our first main theorem here. So the other one, the tropical Bertini theorem, is an immediate corollary of this, following on from the work of mine with Josephine. And okay, so and it goes like this. It's very close, but not exactly the same as the Fuchs-Mantova-Zanier statement. And maybe I can say a few words at the very end, if there's time, about the precise differences. So if we're going to start with a finite dominant map from your variety X to a d-dimensional torus, and let's assume that that does satisfy this pullback property, then in that case, we're going to say that the set of tori with whose preimage, so the set of tori for which the preimage of any coset is irreducible, that set of tori is dense in a Grassmannian. This is, now, what do I mean by dense in a Grassmannian? A subtorus of a torus is given by discrete data. I'm sort of essentially giving you a sublattice of its character lattice. And so I think of that sublattice as spanning a rational subspace of Q to the D. And so I can think about it as dense, as giving me a point in that Grassmannian. And so what I'm saying is that the set of these subtori is going to be dense in this Grassmannian. So again, you can think about this as it's in the same spirit as a classical Bertini theorem. I mean, how do we think about the classical Bertini theorem? We think about it as I can wiggle the hyperplane a little bit, and I'm guaranteed that then that the intersection will be irreducible. And we're saying the same thing. It's dense in this Grassmannian. I can wiggle my hyperplane a little bit, and wiggling my hyperplane a little bit in the Grassmannian wiggles my torus a little bit. And for that wiggled T prime, we will get the preimage will be irreducible. And it'll be irreducible for any coset. It's one of these things that I have to say I don't fully, I mean, I understand the proof, but I don't fully understand why it works that way. It's one of those, once it works for any coset. It almost. Okay, so that's our main theorem. And maybe I'll just give as one example. So this is, and maybe I should say the difference is in the Fuchs-Mantova-Zanier result, they give a finite number of bad tori, and then absolutely everything else is good. We're just saying it's dense. So it's, I mean, it's not literally the same, but it's morally the same as the difference between general and very general, right? We can't give as fine a control over the bad. It's, let's say, and maybe again I can give some hints later. Maybe just as a challenge question for anyone, to give you sort of a flavor, this is just one example. If I took y cubed, the hypersurface defined by y cubed plus 1 plus t1 plus t2 plus t3 in a 4-dimensional torus over f2 bar, so characteristic 2, or your favorite characteristic 2 field. And if I now look at the subtorus given by t to the a, t to the b, t to the c, so just a 1-dimensional subtorus, then I claim that pi inverse of t prime is irreducible unless a plus b equals c. Okay. So this is actually a hint that our theorem is not actually the final theorem for in this world, because this is a stronger, more closer to the FMZ form, that we're saying that there's some tori we don't like, but otherwise they're the same. But in this case, you can see this is a denseness result unless A plus B equals C. So unless you're outside that hyperplane, and well, the Grassmannian in this case would just be P2. Unless you're outside this hyperplane in P2, the pre-image is going to be irreducible. Should say actually, this is making it this precise is stronger than our main theorem. And so I only have an ad hoc proof for this particular case, because this is a special case that we worked out very early in the project. So if anyone can see a very fast way to see this result, I'd be interested in knowing. So that's the challenge for the rest of the talk, is can you see a fast way to know that most of these subtori, the pre-image is irreducible? Okay. It requires some thinking about, of course, I mean, I am not a native speaker of characteristic 2, so it requires some thinking about these sort of things. Okay. But so that's the main theorem of the talk. I'm going to want to spend the rest of the time telling you a little bit about some of the techniques, because one of the things that was surprising about this project was that it sort of took us into some very classical, sort of almost elementary but very hard algebra. So I'll take you on that. I'll take you on a detour via that in a moment, but maybe I should pause for any questions or comments.
I have a question. Is this X smooth?
Is this X smooth? I would think so.
Sorry, you think so or you don't think so?
No, I would think that you're talking about this one, the one. No, the X in the theorem. Oh, sorry, the theorem. In the theorem, no. This is just no smoothness assumptions here. This is So you mean right? So this is at the very start when I said. I get that's actually one reason why I stated my version of the classical Bertini as classical Bertini has two aspects, right? There's irreducible and smooth, and that's one of the distinctions. For example, Kleinman Bertini, there's the smoothness, but you have to worry about irreducible. Here, I want to just focus on the irreducible. You could ask the same question for smoothness, and I don't. Let's see. We'll see in the proof. I haven't thought about the reduction steps. Some of it should go through, but yeah. So if you mean in some sense, if you replace irreducible by right. Sorry, but I should have said irreducible though. You're right. I now understand the question.
You need irreducible.
I do need X to be irreducible. Yes. Right, sorry. So yes, I don't need smooth, but I am missing this hypothesis of irreducible.
When you say dense, what is your topology?
So I want to think about this as a real manifold, well, rational, but think about it as a real manifold here of the Q. Yeah. So dense. So it's really, we're talking about real hyperplanes. I mean the wiggle a little bit. So Euclidean topology on this Grassmannian. Can the tropical Bertini theorem be used to, so yes, so the question in the chat is, can the tropical Bertini theorem be used to prove results by induction? So that was, this is fairly new, so the only thing I know it's been used for was what Josephine and I developed it for. So it turns out the tropicalization of an irreducible variety, it's not just connected, but it's what you might call deconnected. This is in the sense of a graph being deconnected. So you can remove D-1 cells and it still remains connected. And our proof of that is by induction. We basically slice by hyperplanes and reduce to the curve case where deconnected just means connected. And so, I very much hope that there will be other applications inside tropical geometry of this. I think we all agree that the classical Bertini theorem is a very fundamental basic building block. So I very much hope that the same will be true in the tropical world. Okay, more questions? So let me tell you about.
There's a question in the chat that says, can a tropical Bertini theorem?
Yeah, that's the one I just answered. Yeah.
Oh, sorry. Okay.
Yeah. Yeah. Let me tell you a little bit. So this slide is a bit more technical, and then we go back, and then we take a step back to something you could possibly even tell your undergraduates. So let me tell you, but the point of this slide is to motivate why I'm going to start talking about some elementary algebra for a moment. So the key special case of the proof, so maybe again to remind you, I want to know pre-images of tori are irreducible. Key special case is, and this is already the technique, the proof technique of Fuchs-Mentova-Zanier, is you can reduce to the case where X is a hypersurface, and the most important case is where my subtorus is one-dimensional. Okay, so X is just a hypersurface cut out by one polynomial, and a one-dimensional subtorus just is parameterized by x to the n1, x to the n2, up to x to the nd. So I just give you a vector n, and that gives me my subtorus. Okay. Turns out we can also reduce to assuming that this hypersurface, I can regard it as monic in y. Okay, so I'm imagining that my polynomial is given in variables t1 up to td, which are the coordinates on my torus that I'm projecting to, and then one extra variable y. So that's, I guess that was in the example, I had t1 up to t3 and one extra variable y. So imagine that we can reduce to that case. It's monic in y, so I'm just going to factor it. Factor it where? Well, we'll think of it instead of as a polynomial here, think of it as a polynomial with coefficient in y, with coefficients in my field of rational functions. Okay? And then that means I can factor it over the algebraic closure. So I'll factor it as a polynomial, my product of y minus alpha I, where the alpha I are elements of my field of, elements of the algebraic closure of my field of rational functions. Okay. The pre-image of my torus T prime, this one-dimensional torus, again, that just means substitute in T1 equals x to the n1, T2 equals x to the n2, up to Td is x to the nd. I substitute that in, and I'll get a polynomial in x and y, which I'll just call g. So now I have a polynomial in x and y. My assumption that f was monic means it has the same degree in y. I didn't cancel anything. And I can factor that as well. And now my roots beta I are, they're going to live in the algebraic closure of the field of rational functions in just one variable, just x. And roughly the hope is that the beta I can be obtained from the alpha I. Okay, that's what I'm going to explain to you, how to try and make that hope real. Why is that the hope? Because we're starting with the assumption that if I start with the assumption that x is irreducible, so f is an irreducible polynomial. Okay, so that means in particular, none of these alpha I are actually polynomials. And also, you can't factor f. So if you tried to factor f, taking the product of some subset of these, the coefficients are going to be symmetric functions in the alpha i's. So you need also maybe enough of the symmetric functions in the alpha i's are also not polynomial. So we know that that's not the case. If we want to know that g is also irreducible, then we want to know that the same is true for the betas. So none of the betas should be polynomials in x, and so on. Okay. And if we can get the betas from the alphas, then you can maybe control that. You can say, if I do this sort of, we get g from f by a simple substitution, ti equals x to the ni. If we can get beta from alpha by a simple substitution, then we could maybe control whether the betas are polynomials or not. Okay, so that's the loose plan of attack. I'll come back to this. But what it motivates is thinking about these two fields. Okay, it says it would really be good if we understood a bit better these fields of rational function, algebraic closure of the field of rational functions. I have to admit that until, well, in tropical geometry, we're forced to think a little bit about this. But until starting this project, I have to admit I had not thought at all about this, and I'm going to assume that the same is true for most of you as well. Okay, and it's surprising for something that you could, in principle, write down in a first or second serious algebra class to undergraduates. We know surprisingly little about these. Okay, so let me now take a step back, and this is sort of a re-entry point if anyone's got has this talk playing in the background while they handle their email, to sort of come in as a reboot. Okay, so let's come back and think about these algebraic closures. Okay. One of them is, well, not the algebraic closure itself, but close to it is very classical, centuries old. And that's, in characteristic 0, if I give you a polynomial in x and y, monic in y, then I can factor it over and it has roots in the Poisson series. So the Poisson series are just, I can think about it as the union of Laurent series in x to the 1 over n. So I have series in x, I'm allowed fractional exponents, but my fractions all have to have a common denominator, so for some value n. Okay. So this sentence is saying that the algebraic closure of the field of rational functions is contained in the Poisson series. Okay, it's not equal, but it is contained in it at least. Okay, and so this fact goes back, quite a long time. It's called, the algorithm to actually compute the alphas given x. This is the Newton-Poisson algorithm. Maybe why we think where Newton polytopes come from. Yeah, so it goes, hundreds of years old in various, well, depending on how you interpret it, and applications. It comes up in many different parts of mathematics. Okay, so in some sense, we know an answer in one variable. It's not quite the algebraic closure though, but it does the job a lot. I will make the observation though, this is, you could ignore this, but it's slightly relevant in a few slides, that there is a convention choice, and we never really think about this, right? There's a convention choice to work with series that go upwards. When we talk about Laurent series, you say it's bounded below, but we go upwards. But we could work with the opposite thing, bounded above and go negative. So we could work with Laurent series in x to the negative 1 on n, take the union of those for all n. This is also an algebraically closed field that contains the algebraic closure of rational functions. To give you an example, and if this is a fact you've never seen before, this is probably the elementary takeaway fact from this talk, is if you think about 1 over 1 minus x, if I asked you to expand this as a series, 95% of you would write 1 plus x squared plus x cubed, etc., etc., etc. Okay, but you could also say minus x inverse minus x to the minus 2 minus x to the minus 3, etc. Okay, if you've never thought about that before, I encourage you to multiply the series by 1 minus x and check that you do actually get 1. Right, so you just have to set up a ring where that multiplication makes sense. Okay, you can't, of course, have a field that has both of these in, because then we'd have these two different meanings. So you have to sort of choose a convention choice. In this case, the convention choice is I'm going to take positive exponents eventually or negative exponents eventually. Okay, and we'll see how that generalizes as we go to more variables. Okay, so that's characteristic 0, one variable. Poisson series, centuries old. When characteristic of k is p, is positive, then though Poisson series are not algebraically closed. Okay. This was first pointed out, I think, by Chevalier, who said this Artin-Schreier polynomial. So y to the p minus y plus x inverse. If I think about this as rational coefficients and rational functions in x adjoin y. So this has no root in Poisson series. Okay. Then Abianca pointed out that, well, if I relaxed my definition of Poisson series is a little bit, then I would get roots. So in particular, this f is the product of, it factors as y plus I, as I varies, plus a sum of x to the 1 over p to the I. So if p were 2, this would be x to the half plus x to the quarter plus x to the 8th plus x to the 16th, etc. Okay. This is not a Poisson series, right? Because for a Poisson series, for any given series, you have to the exponents have to have a common denominator. And here I'm letting my exponents get larger and larger. So my denominators rather get larger and larger, but they are all powers of p. Okay, so in general, I'm allowing for generalized Poisson series in this sense, and this again is an algebraically closed field. I'm going to allow series with exponents of the form m over n times p to the I, where n will be fixed like it was in the Poisson series for a given function, but the powers of p can vary. So I might have something like, this is for p equals 2, x to the 3rd plus x to the 1 plus the 6th plus x to the 2 plus the 12th plus x to the 3 plus the 24th. And you can see that my denominators all have the form 3 times the power of 2. Okay, so that's what I'm allowing in this case. And just to, so again, there's a power of p, and p should be the characteristic of the field. That's allowed to grow, but for fixed p, but for a fixed series, anything that's not a power of p should just remain constant. Okay. So that's the generalization of Poisson series that works for characteristic p. Okay, so comments, questions? Okay, so that's one variable. So we've done one variable characteristic 0, very classical. One variable characteristic p, mid late 20th century. I think this field, working out the field of this is a paper in the, well, one reference is a paper by Rayner in the 60s. So, okay. Now we come up to the last 20 years or so, and this is, let's think about multivariate analogs. Okay. So what we want to do now is look at series. The idea is roughly, we're going to pick a direction, and I'll look at series supported in cones that lie on this, go in that direction. So lie on this, on the same, that direct side of a complementary hyperplane. So we've got cones that lie on one side of a hyperplane, and we're going to, the same condition on denominators. We're going to allow denominators of the form n times p to the I, where p is the characteristic of my field. N is going to be fixed for any given series, but the powers of p can vary. Okay, so here's an example where the cone is going to be just the positive orthant. And my series might look like something like 1 plus x plus y plus x to the 3rd times y to the half plus x to a 3rd times y to the quarter plus x cubed times y to the, I cannot read my own writing to know whether I think I meant an 8th there, a 6th would also work here. The idea here that I'm allowing my denominators are all can we all be written in the form 3 times the power of 2. Okay? And there's an extra actually technical assumption that I'm not telling you, that the set of exponents that show up have to also be well ordered. So this is a standard thing that shows up in these sort of generalized power series conditions in order to make multiplication well defined. So I need there to be a direction in where all of the supports of my series, so the exponent vectors, all live in a cone that's positive on the positive side of that hyperplane, and they all have the denominators all have this form, powers of n times the power of p, and that they're also well ordered. So this is in characteristic 0, so without the powers of p. There was, some of the combinatorics of this was worked out by MacDonald, Arrocha and Naladi. I think I'm choosing the right reference here, who wrote down the field explicitly, and then this was generalized to characteristic p in the same way as the series we saw on the previous slide by Saavedra, who was Arrocha's student. Okay, so this gives us a new and I guess at least all of, well, implicit in all of these are definitely in the last, Saavedra's the most recent paper from again about 5-6 years ago, proved that this field is algebraically closed. So this gives us an algebraically closed field that contains rational functions in D variables. Okay, so that's good. Again, it's not the algebraic closure, it's larger, but it at least is an algebraic closure. Okay. So let me come back and remind you why I cared about this. So my proof, so this is essentially from the previous slide, right? We were trying to decide that we had a hypersurface given by a polynomial f, and we wanted the preimage of a one-dimensional torus to be irreducible. So that meant we were going to substitute in ti equals x to the ni into my polynomial to get a new polynomial g in x and y. Okay, I factor f to get the roots alpha, which we now know I can think about as multivariate Poisson series. I factor g and I get at roots beta, which I now know I can think of as these slightly generalized Poisson series in one variable. Okay, depending on what the characteristic of k is. Right. I guess I should have said, sorry, I made one comment. This direction, so this field, this description depends on a direction. And you should think about this as the multivariate generalization of the observation I made here down the bottom, that there are there's a convention choice for series in one dimension. You either go positive or negative. When you go to more variables, there's now an infinite number of choices corresponding to a direction vector in there. Okay, so what are we saying? We have our hypersurface f, it factors with roots alpha. We have a hypersurface, we now have a polynomial g, it factors with roots beta. We would like to obtain beta I from alpha I by just doing the same substitution that we do to f to get g. Okay, we would like to just substitute in ti equals x to the ni. Okay, the problem is because in characteristic p, the support of these series is not discrete. You can have accumulation points. And maybe what's going to happen is that when you do this substitution, you can think about it sort of combinatorially geometrically on the supports as a projection. You might end up adding up an infinite number of terms. Okay, it might be the case that when you have the series has an infinite number of the series alpha I has an infinite number of terms. And it might be that when you do the substitution, an infinite number of them all turn into x cubed. Okay, and then you don't know what the coefficient is. So the problem is that the substitution map might not be well defined. I mean, this should not shock you, right? Because if there were a substitution map, you'd have a homomorphism of fields, so you'd be embedding this field into this field. Yeah, so the fact that it doesn't necessarily work is not horribly shocking, but it's disappointing from the point of making it work, because if we could do this substitution, then we just have to say, well, I look at alpha, I look at what terms show up in alpha I, and one of the things I want is that alpha I, when I do the substitution, does not turn into a polynomial in x. So I need to just make sure that it remains a series, that it's not a polynomial, because I want this not to factor once I do the substitution. And so our contribution, so this is sort of the main result of our paper, in some sense, is we construct an explicit algebraically closed field that's smaller than Saavedra's, than these multivariate generalized Poisson series, but it's still algebraically closed, so it still contains the algebraic closure of the field of rational functions, so that this does work. Okay, so that you can, so that you know that if I have a root, so that what I said might go wrong, if I have an alpha I, when I try and plug in ti equals x to the ni, I know that I will never end up adding up an infinite number of terms. So we can define a substitution map, and it turns out that that will then turn into these roots beta I. So that's the sort of so most of the paper with the however many the 7 author paper is constructing this algebraically closed field that is part of an algebraic, it's an overfield containing the algebraic closure of rational functions, but smaller than the previously known ones, so that this plan of attack works. And maybe I should just finish by observing that I think it's still very open to understand the difference here. I mean, in some sense, this is still, there is a lot more work in one variable here of understanding this question of, because there's 2 parts to this question. You can ask about the support. So you can ask, if I look at the series, what type of exponents show up? And then you could also ask for the coefficients. And so there's some work on the exponents. So our work is basically all on the support. At our new field, we observe that you can put constraints on the supports of series that show up, more than just that they are well ordered and have denominators of this form. And the resulting field will still be a field, will still be algebraically closed. And our plan of attack works. But you can also ask questions about the coefficients. And there's some work on that, mostly in one variable, a tiny little bit in 2 variables, but mostly they're over finite fields of, saying, what type of coefficients will show up. And there's sort of theorems about them being p automatic, or basically being given by some cellular automator. So there is some work, it's very intriguing, but I think it's still widely open. And until I guess this always happens in mathematics, but for me, this was one of the more weird projects that I thought I was starting with a very well-defined tropical geometry problem. It led me into some fairly deep fundamental algebraic geometry, and then to this, in principle, elementary but hard algebra. So it's sort of one of these weird mixtures. I think I'll leave you with this intriguing question of whether you can understand the algebraic closure of rational functions, having hopefully convinced you it does have something else to do with algebraic geometry along the way. So we'll stop there. Thank you.
Thank you. We have some, we have very little time for questions, but I think it's unfair not to have any if people have questions, and Diane is happy to answer. So does someone want to ask something or make a comment?
May I ask a question?
Yeah, of course, Martin, of course.
Yes. So I'm sorry, I have a problem with my Zoom. Just a second. Yes. Thanks for the talk. Very nice result. So I'm mostly interested about this Bertini theorem of Fuchs, Diane, and Mantova. So my question is about not this. Of course, there is this important issue of seeing the genericity, no? As you mentioned, one expects rather to have this, except generic situation, not a very generic situation needed for that. Exactly, that theorem, or indeed yours, if you want. No? My question is about the variety you're considering, the X who is projecting into this torus. So it is the hypothesis, it is dominant. And this is something I have seen this theorem before. I mean, the Fuchs-Mantova.
Well, we relied on your paper to understand.
Yeah, we have common interest. This is great.
Yes.
So there is this hypothesis of dominant, which somehow bothers me of this, because and indeed I wonder how you deduce. Of course, I got lost at some point. How you deduce your tropical theorem with that abstraction, because just to be trying to be clear, I am not very clear, I'm sorry. In the Bertini theorem, you have a subvariety in the standard one, the subvariety that you intersect with a hyperplane, for instance, no, with a linear subspace. And this is not quite the situation here. You have a projection to a surjective projection to a torus. Okay, so I would be happier indeed. I mean, I would be happier with the analogy if one has like a toric Bertini theorem, which is for subvarieties. Okay,
yeah, no, I agree. I mean, well, I mean, I know that you know this, but maybe I'll just bring everyone else along for the ride. I mean, we can think of it. So at least I think about often my case is where X is itself a subvariety of a torus, of say an n-dimensional torus, and the projection comes, the map comes from a projection of tori, and then you can, then you can take your torus downstairs, your T prime, pull it back to T to the n, and do the intersection upstairs. And I mean, we can reduce to that in these settings at least. So we can see that this is a special case, but on the other hand, it is somehow a special case of which subtori you're allowed to think about, the ones that come from pre-images of projections, dominant projections. And I completely agree. That was, I mean, when we started this project, that was one of the questions that we thought we would think about, and then we didn't. We didn't end up having anything to say. But I agree that would be the natural question. Yeah, so I agree. This is not the final. This is not a final version of this theorem.
Of course, no. I'm happy this keeps the subject going on. So if I understand correctly what you said, you agree that with this kind of theorem, if you have a subvariety, you have to project into one of the direction onto which it is dominant, and then you can take subtorus that come only from that direction. Okay, I agree.
That's right. Yeah. Yeah, so it's it's a little. I agree. It's a bit unsatisfying. I would like a nicer version.
Oh, okay.
I mean, it might be reducing it might not be too bad, right? Because you could always, you can get more subtori, right? Because you could always imagine projecting your subtorus and your variety into a dominant thing, and checking whether the projection is nice. So, but yeah, no, I agree. It's not. I completely agree, and this was also on my list.
Okay.
Yeah, but I don't have an answer for you. Yeah.
Okay. But so sorry if so coming back to so this is not an abstraction for you to deduce your tropical theorem.
No, because you've got your tropical theorem, you can always just project. I mean, tropicalization plays very nicely with projections. So you can, we can restrict us. I mean, we can reduce it. So what this means upstairs is that you're only going to look at hyperplanes that have, that have a kernel that's orthogonal to a direction where the projection is dominant. But that's not a serious obstruction, because most,
Okay, thanks.
May I ask a question?
Yeah, go ahead.
Okay, so okay, maybe it's a very naive question anyway. One of the most classical applications of classical Bertini theorem is the fact that if you have a linear system in a variety, then the general element of this linear system is moved outside the base point. This comes from the fact that the element becomes a hyperplane section under a suitable projective embedding. Okay, so do you have something similar in this tropical and toric settings?
So are you particularly interested in the smoothness or so this is why I was trying to make this distinction at the start between, here I was only going to focus on the smoothness, on the irreducibility. I think the smoothness in the toric world, I mean, maybe Martin, have you thought about this? I mean, I think the smoothness probably might come through because, you know, when you, but I didn't think through the reduction to the hypersurface case. Once you're in the hypersurface case, you're essentially asking the question, if my polynomial upstairs has simple roots, will it have simple roots downstairs? So I think it's not written down, but it's the toric version is plausibly true. Smoothness in the tropical world is harder to think about. I mean, you have to decide what you mean by smoothness, and there's a bunch of possible different answers. But yeah, so I don't know whether that was an answer. Yeah, answer you.
Okay, thank you very much.
Okay. Any more questions or comments? No? All right. Well, thank you very much, Diane. And we'll see each other next Tuesday.